Hello, good day everyone. I'm Tushara Jayasinghe, a PhD student working with Dr. Wijewickreme at UBC Vancouver, Canada. I'll be presenting part of my PhD research work on the topic Some Observations on the Shear Strength of Organic Soils. For this presentation, I will quickly go through an introduction to the presented research work and then field and laboratory experimental test program that we have followed here, and followed by a shear strength result comparison, and I will wrap up the presentation with the summary of the work. Moving on to the introduction, first I will introduce the soil that our research work is based on. Organic soils, which are also called muskeg or peat, are partially decomposed plant matter usually found under the water table, which is high in fiber and water content. When Canada is considered, 18% of the land area, 18% of Canadian landscape is covered with organic soils, and more importantly, many pipelines cross these parts. When the mechanical behavior of muskeg is considered, it is known to be a problematic geomaterial due to various reasons. As I have indicated here, characteristics such as high compressibility, high void ratio, and high water content, and low shear strength and weak stiffness properties govern the behavior of muskeg. So unlike for mineral soils, no significant research have been carried out to investigate the mechanical behavior of these soils, including shear strength behavior, which plays a major role in pipeline design work, which we are interested in. So for the design of pipelines, we perform soil pipe interaction analysis, and usually soil, as represented here, soil is represented as a group of springs in vertical, horizontal, and axial directions. And we define load displacement or soil spring curves to analyze the behavior of the surrounding soil when the pipe is buried. This is done using different guidelines. Some examples are ICGE2020 ALA and PRCI guidelines, depending on the type of soils. If we take axial soil springs as an example, and the design criteria mentioned in PRCI, axial shear resistance developed at a given soil pipe interface is based on either undrained shear strength or the interface friction properties at the soil pipe interface. So when we are concerned about organic soils, undrained shear strength plays the major role. Therefore, when organic soil is considered, undrained shear strength is used in defining the soil springs or load displacement curves for soil pipe interaction analysis. So keeping this in mind, we have conducted a comprehensive field and laboratory experimental program to characterize muskeg for pipeline design work and use the resulting parameters as input in numerical modeling of soil pipe interaction along the way. So for the field investigations, we have selected the site crossed by pipelines that are in operation. This site is located in Surrey, British Columbia, in Canada, and the specific location of the test site is indicated in the map on the left-hand side. And for the base of the map, I have used a surficial geology map of Metro Vancouver area, and also a site layout illustrating the test locations and test groupings is also shown on the right. So for the field test program, we have done in situ seismic cone penetration tests, electronic vein shear tests, bore penetration tests. And also for the laboratory tests, we have extracted some bulk samples using auger sampling, and also relatively undisturbed samples using Shelby tube sampling. All the details of the equipment dimensions are listed in the table, and I'm not going to go through the table, but these are the we have used standard size equipments for the field testing program. If we move to the laboratory test program, we have conducted tests to determine the index properties to characterize and classify the soil. According to soil classifications, the tested organic soil is identified as amorphous peat. So these properties are interrelated, and they all these physical properties affect the engineering behavior of an organic soil to a great extent. So if we focus on the water content, it is in the range of 350 to 650 percentage within a depth ranging from 2 to 7 meters. In addition to index testing, we have conducted laboratory monotonic direct simple shear tests, DSS tests, on reconstituted specimens prepared from bulk samples, which are extracted from the site. So I have shown here results of 2 DSS tests conducted on specimens with initial consolidation pressure of 20 to 30 kp, 20 and 30 kPa corresponding to 2.1 and 3.2 depths, depending on the bulk density found at the site. SU values interpreted from the field tests along with the laboratory tests are presented in these figures for test groups 1 and 2. The cone and the ball penetrometers give continuous SU profiles, and the cone exhibits a wider variation of interpreted undrained shear strength varying from 10 to 40 kPa for the test group 1 and 10 to 75 for the test group 2. It appears that the local variations, such as variation of the presence of fibers in the soil, is reflected in the measured resistance. The range of SU values interpreted from ball penetrometer varies from 20 to 50 kPa for both test groups, and they display fewer local variations compared to the cone penetrometer. And SU values from ball penetrometer seem to be in good agreement with those from the vein shear tests, and which can be seen from these 2 figures. And the SU values extracted from the laboratory monotonic DSS test results are also superimposed in these figures for comparison, and the lower SU from the laboratory DSS tests are likely to be due to sample displacement and sample disturbance and change in soil fabric during sample reconstitution. So moving on to a summary of findings, initial findings suggest that the ball penetrometer provides a suitable way of estimating undrained shear strength of organic soils as it mobilizes a relatively large volume of soil mass during penetration compared to the cone testing, and that is preferable to characterize organic soils, particularly considering their variable nature and low strength and stiffness properties. This is also aligned with the previous findings of various researchers, including Boylan and Michael Long. Also, soil anisotropy, strain rate effects, sensitivity of the testing tools to the soft nature of the soil should be accounted for when selecting N factors when converting penetration resistances to undrained shear strength. It is also should be noted that penetration tests in soft organic soils are likely to be influenced by partial drainage effects related with the rate of penetration, and these effects have to be critically considered when interpreting the strength parameters from the penetration test, especially in organic soils, which are soft and weak in strength. Thank you very much.